So now that we've introduced L'Hopital's rule, what we're going to do next is take a look at some indeterminate quotients. First, we're going to try out the limit as x approaches 2 of the sine of pi x over x squared minus 4. Now, just to make sure that everything's working the way that it should, first thing I'm going to do is just try to use the direct substitution property just to make sure that what I claim is an indeterminate form is actually an indeterminate form. So I'm going to try to plug it in, x equals 2. Up top we get the sine of pi times 2. Sine of 2 pi is equal to 0. And in the denominator we get 2 squared minus 4. 2 squared minus 4 would be equal to 0 as well. So yes, indeed, we have our indeterminate quotient. Now because it's already an indeterminate quotient, we're allowed to go ahead and apply L'Hopital's rule. L'Hopital's rule says go ahead and take the derivative of the top and the derivative of the bottom. For the derivative of sine of pi x, we'll need to make use of the chain rule. Derivative of the sine function is the cosine function, and the derivative of the inside is the derivative of pi x with respect to x. That would be just pi. In your denominator, derivative of x squared minus 4 is going to be 2x. Now, if you attempt to use the direct substitution property again at this point, we'll get more favorable results. This will be the cosine of pi times 2, we'll call that 2 pi, times pi, over 2 times 2. Simplifying the numerator, the cosine of 2 pi is equal to 1. 1 times pi will be pi. And the denominator is 2 times 2, which I plugged into my calculator, aka brain, and got 4. So final answer for this indeterminate quotient would be pi over 4. Try doing that using algebraic manipulations from back in chapter 2. Can't do it. Next one. We'll try this indeterminate quotient. This is the limit as x approaches 0 of the natural log of x plus 1 over e to the 2x minus 1. Once again, we'll try that direct substitution property, and we'll just plug in x equals 1. Numerator becomes natural log of 0 plus 1, and the denominator is going to be e to the 0 minus 1. Natural log of 1 is 0. 1 minus 1 is 0. So we do have an indeterminate quotient here. We're going to go ahead and apply L'Hopital's rule right away. Take the derivative of the top and the derivative of the bottom. Derivative of the top would be the derivative of the natural log of x plus 1. That'll be 1 over x plus 1. Chain rule says then multiply by the derivative of that inside. Derivative of that inside is 1. In the denominator, the minus 1 is going to go to 0. E to the 2x. Derivative of e to the is e to the. Then the chain rule says multiply by the derivative of that exponent. That'll be 2. You might be tempted to fix the fraction inside of the fraction at this point, but I'm going to let you know there is no need whatsoever. We're just going to go ahead and apply the direct substitution property and plug in 0. That'll be 1 over 0 plus 1 times 1. That's going to be 1. Your denominator will have e to the 0, which is 1, times 2, and we'll have 1/2 for a final answer. Trying out a couple more examples. Next one we have, limit as x goes to infinity of 6x squared minus 7x plus 5 over 3x squared minus 8x plus 5. You may recognize this from back in chapter 2 as a limit at infinity, where it goes to infinity over infinity. Now just to make sure, if we attempt to use the direct substitution property, we can't really plug in infinity, as it were. But your numerator is going to go to infinity and your denominator is going to go to infinity. Now, we have a technique from back in chapter 2 that will work. In chapter 2, we would have said identify the highest power in the denominator and then divide top and bottom by that highest power. So if you wanted to proceed by dividing top and bottom by x squared, you would get a favorable result. Let's be honest about that. However, if you do attempt to use L'Hopital's rule for this, we'll get a favorable result as well. So we differentiate the top. It'll be power rule all the way across. 6 times x squared would be 6 times 2x. Minus 7x would become minus 7, and plus 5 goes to 0. For that denominator, 3x squared would become 6x. Minus 8x will become minus 8, and plus 5 will go to 0 as well. Now, if once again you were to allow x to go to infinity, the thing that we would point out is that your numerator is still going to infinity. 12 times infinity minus 7 would be infinity. And 6 times infinity minus 8 would still be infinity. So it still takes on an indeterminate form. As a result, our response is going to be, let's use L'Hopital's rule again. it is possible that you could potentially see multiple uses of L'Hopital's rule. I had a class wrong me once and I made him do 6 in a row. Don't worry, I'm not that mad this semester. Derivative of 12x minus 7 is going to be 12. Derivative of 6x minus 8 is going to be 6. And at this point, there's really no direct substitution property to do. We would just wind up with 2. Now, if we had gone this route, then the only non-zero term after we let x go to infinity would have been 6 in the numerator and 3 in the denominator. That would have simplified to 2 as well. And last example. The limit as x goes to 0 of the sine of x over 1 plus the cosine of x. First thing I'm going to do is attempt to use the direct substitution property just to make sure it's an indeterminate form. Numerator is going to be the sine of 0, which is, of course, 0. And your denominator is going to be 1 plus the cosine of 0. Cosine of 0 is equal to 1. 1 plus 1 is... Well, you know what? I guess this one isn't indeterminate. This one was just direct substitution property. Now, am I the kind of guy who would try to fool his students with something where you don't actually have to use L'Hopital's rule? Would I do that? Yes. Yes, I absolutely would. Always try the direct substitution property first.